Good morning, everyone. I'm very happy to have this chance to share my understanding about this title. It's the upward or the downward transfer of the sulfide in a magmatic conduit system. Firstly, the story about the magmatic nickel copper sulfide deposit start with the Sudbury basins, and about 15 deposits has been found around the Sudbury complex, and the earlier explanations is direct to the large scale layer intrusions, but no very good result. So, and finally, we found that the people found that it formed by impact. It's not a common example. And then, thanks to so many years work from the Tony Zhusi and Steel and that on the Norilsk on Jinchuan and the Walls Bay deposits, now people's understanding about the formation of the nickel copper deposit comes to a conclusion that it forms in a dynamic magmatic conduit system, except some chromatia associated deposits. But there are still so many problems remain. One of the most important problem is that it means the sulfide mass of the ore base is usually far larger than the amount of the sulfide that can be segregations from the host intrusions. And people felt there are two possible solutions to these problems. One, they think the sulfide is segregations from a large volume magmatic system above the ore base. And some people think it's from deep-seated magma chambers. And at the beginning of this research, I think Tony Natrick and Viscosity also stand for these ideas. But now many people maybe also support the ideas of the first one. And the first one ideas require the downward transport of the sulfide in a conduit. And the second one requires the upward transport of the sulfide in a conduit. Why I think there's good questions, because during my submissions of my papers, some reviews or other people will ask, they don't think the upward transport of the sulfide is possible in nature. So I think today may be a good time to have a detailed discussion on these issues. Firstly, we should think about the physical properties of the sulfide and mass. This is a table from the Robinson JP papers. We can see that the sulfide has a very high density and a very low dynamic viscosity, then relative to the chromatia, to the basalt and the dacite. And we can also see that this figure shows the possible range of the dynamic viscosity of the chromatia of the basalt, andesite, and dacite, and the rhyolite. And just in a short conclusion, we can find that the sulfide liquids has a high crystallization temperature. This means the sulfide mostly remains in the liquid state in the metric system. Secondly, it has a high density. It's larger than the chromatia, basalt, and involved in the cumulus melts. And it always has a downward settling tendency. And thirdly, it has a low viscosity. It's very small than the chromatia, basalt, and easy to transport in the system. And finally, it has a high thermal conductivity. It's easy to hit the country rock. And secondly, we should rethink about the fluid dynamic environment of this system. The fluid dynamic conditions of the magma flow is determined by the Reynolds numbers. It's defined as the ratio between the initial and the viscous force. Here, I just collect maybe 16 parent magmas from different deposits and calculate their Reynolds numbers. And we can find that the basalts and also the arc-related basalts mostly fall in the region of the laminar flow. Laminar flow means, like these figures, it's just the flow is very slow, and the magma just flow along a layer, and there is no interaction between the neighboring layers. And the flow of commodities and the pyrite basalt always following the region of the turbulent flow. Turbulent flow is very complex. Its flow direction and its flow velocity is highly variable along with the time, like this. Because the conduit system mostly focuses on the metric system. So I think the laminar flow may be suitable for the question here. And thirdly, we should think about the form of the sulfide liquid in this system. This is a model from the Robinson. He thinks that this is for the deformation and the breakup of sulfide droplet in a strong laminar flows. And this droplet, this sulfide droplet will break up into so many doctor sulfide droplet. And it's also, there are new models. We can see that this is a static massive sulfide pores, and there is a magma flow along these directions. And we can see that this magma flow will break up their interface between the magma and between these sulfide liquid pores. And this breakup will finally form so many small size of the sulfide droplet. So we should think that in a dynamic conduit system, the sulfide liquid should mainly occur as a small size droplet, except the massive sulfide liquid pore can just stable when the system is very close to a coarse static state. So finally, the problem is simplified as the two main contents. One is we should think about the physical transport of the sulfide droplet in a dynamic system, just like upward ascending magma flow here. And another thing is the physical transport of the poured sulfide liquid in a static conduit system. Firstly, we think about the sulfide droplet. This is a figure from the Bowen, and he firstly observed the free settling of the crystal in a static magma maybe 100 years ago. But here, I should borrow the ideas from the physics because the form of the reference. Because whether or not you are moving is most dependent on your point of the view. So we're just thinking about the settling of the sulfide droplet in a ascending magma flow. Because in master conduit system, the setting velocity of the sulfide is far less than the ascending magma. So if we stand the viewpoint of the ascending magma, we should think, oh, the sulfide droplet and also the wall rock are both settling. But if we setting the viewpoint of the setting sulfide droplet, the magma and the wall rock are all ascending. And the most important thing is if we thinking the viewpoint of the wall rock and is a static wall rock, the sulfide droplet still have an upward transport with the velocity equals to the V2 minus V1. So I think if we just thinking about the single sulfide droplet in ascending magma flow, it's very easy to take upward transport. Yeah, it's just dependent on the frame of the reference. And secondly, we should be thinking how many sulfide droplet can be carried by the ascending magma flow. Here is Steve's ideas. He just thinking about the density. He think just if we take a basalt and this basalt can carry maybe 5% of the sulfide, and then this will exhaust the buoyancy of the basalt. And if this basalt also contained 10% of the olivine, so it's just maybe 2 or 3% of the sulfide can just be carried. But in my opinion, the countering factor about the magma flow and the magma deck propagations is not the magma density. It's just dependent on the magma overpressure, And secondly, the viscosity related fractional force over the flow is not considered here. So I just build up a model to just model variation of the magma overpressure along this magma joint. We can see that if this system have no excess overpressure, and we just thinking about the magma buoyancy and the flow fraction, we can see that if we just take a basalt, and when the basalt have contained 5% of the olivine, this overpressure have exhaust. So the maximum of the sulfide of the olivine is just 5%. And if this olivine changes to the pelagicals, because pelagicals have very less density, so this basalt can carry about 33% of the pelagicals. And if we thinking about the sulfide, because sulfide is also denser than the olivine, so it can just carry about 2.8 volume of the sulfide to take the upward transport. And if the basalt also contain olivine, so it can just take a 1.9 volume percent of the sulfide. So if we just thinking here, the magma cannot carry so many sulfide. It's just maybe less than 5% of the sulfide in the ascending magma flow. But if some process in the magma chamber can drive an excess magma overpressure, like maybe a new replenishment of in the magma chamber, it maybe can give a very large magma overpressure. Here we take an example from the mollusk. We know this is the section of the basalt, float basalt in the mollusk regions. We can see this basalt can derivate in 3 stages. And we know the second stage occurred the crystal accumulations in the magma chamber and get the sulfide saturations in the magma chambers. And finally, the emplacement of the deposit is occurred in these regions in between the MR to MK basalt. So here we just use the volume of these 2 stages, the second stage of the float basalt, to calculate the initial volume of the magma chamber. And then a new replacement of the MR/MK, and we can calculate that their change of the volume. Here is these values, and then we can calculate this replacement of the MR to MK basalt can drive maybe 22 MPa of overpressure. And this overpressure can carry 10% of sulfide beside 8% olivine and 1% pelagicals. All this can be carried by this MR to MK basalt to take the upward transport. Beside this excess pressure, it also something is the water's effect of the water on this transport of the sulfide droplet. Firstly, if we add the water in the melt from 0 point to the 3 point, it will strongly decrease the melt density and increase the magma buoyancy, and it can carry so many sulfide droplets. And secondly, it can decrease the melt viscosity, and it's also weaken the flow fraction. And finally, dirtiness transport, and in the slow dip, this water or this will solutions to form the vapor bubbles. We can see that, if the system have contains 3% of water, and this will form formation of the vapor bubbles, it may be 3,000 kilometers deep, and it will quickly decrease the magma density and slightly increase the magma viscosity. And finally, they will strongly increase the magma overpressure. So the addition of the water or the CO2 will strongly increase the carrying capacity of the sulfide droplet. So this is the model related. You can see that from 1% of the water to 3% of water, the load of the sulfide can increase from 5% to 13%. So this is a very important thing to suitable the upward transport of the sulfide droplet. And finally, is all James' ideas talk about the compound drop. When the sulfide melts and the silicate melts and the vapor bubble, they enter into the same system. And the vapor bubble will tend to attach to the sulfide droplet due to the surface tension effects. Here is I draw the figure of the equilibrium state of the this three-phase system. And if we take a reasonable surface tension between the magma and the sulfide, and this blue regions is representing the possible regions for the compound drop in the magmatic system. And we can say most part is falling in the region of the compound drop. And also the compound drop have been found in many experimental work and also in the nature samples. So more and more papers to think that the fluid can be the powerful carriers of the sulfide to take the upward transport. But I think still some people will think it's not the real stories because they think the sulfide is too dense and the vapor cannot float it. And secondly, the compound drop is not stable, maybe in a dynamic flow. And the third, its interaction with the crash machine, and no one talk about this. And firstly, I just calculation the density of the compound drop. You can see that if we change the shape of the compound drop, their density will change from here, increase to here. This region is the density of the melt density. So we can see that most part of this the compound drop, its density will less than the density of the melt. So it means the compound drop have contribute a lot of buoyancy to do the upward transport. Secondly, we should think about the stability of the compound drop. Here is just I moved in the result. It also have different shape of the compound drop, and this is different size of the compound drop. We can see that in this yellow range, the compound drop will stable, but if it enter into the pink range, it will separate. Here is a movie to show the separation between the vapor bubble and the sulfide droplet is very clear separations. So we can see that if the sulfide droplet, if the compound drop have the same shape, just like this line, and if we just increase the size of the sulfide, of the vapor and the sulfide, just from here to here, and the compound drop will from the coupled to the separate. And the analysis, if we just thinking that is the same size of the compound drop, but if just we changing the shape of the compound drop, we increase the sulfide size, and the compound drop will always separate. So, but we must say that the compound drop still remains stable, but all the model is just based on the static system. And there is physical papers talk about the dynamic system, how the deformation of the compound drop in different capillary numbers. We can see that if the compound drop have a high capillary numbers, maybe larger than 0.25, the sulfide and the bubble will separate, and this deformation of the sulfide, the compound drop. Here, I just follow their ideas and molding the version of the density and the velocity and the capillary numbers of the one compound drop in a conduit system. And we can see that when the system go into a very slow system, a slow dip, the capillary number of this compound drop will quickly increase. And then finally they break up. So I think it may be actually also good for the all-forming system, because in a slow dip, the air and the sulfide will easily to break up, to separate. And then the vapor bubble will go to the air, and maybe the sulfide droplet will doing some settling and then finding a suitable place to form the final overlays. So this is just talk about the study of the compound job. Finally, it's just modeling the transport of the compound job in a question mesh. I just passed from a post road like this. Sorry. This is the modeling result. Some cases, this compound job can safely transport this post road, but sometimes it cannot transport, and it will also give a clean separation between the vapor and the sulfide droplet. Here is also the regions for which condition it's the sulfide can pass, the compound job can pass through this crest mesh, and this part, these small cases, the sulfide and the bubble will separate. So finally, we have a small conclusion about the compound job. So firstly, it mostly has a density lower than the host melt. Secondly, it can pass through the static crystal mesh. Yeah, sometimes it can pass through. Thirdly, is very important. It can just stable in some condition of the static system, but it can easily break up or decouple in a faster flowing magma at a very slow dip. I think it may be the bubble maybe work as a rocket, and it carries so many sulfide droplets and go to the upward. And when in slow system, and the bubble think, oh, my work is full, and I pick up, I separate the sulfide and let the sulfide to form all bodies. To be honest, at the first of the beginning of this work, I'm also not confident in this in the formation of the compound job. And here is James take me to see the industry, to see the filtration of the sulfide oils. It's very similar with our work here. You can see, oh, this is the bubble, and around this bubble is the sulfide. So it can flotation of the sulfide oils like this. So I think it's also stable in the nature system. Finally, I think we should talk about the physical transport of the poured sulfide liquid in a system, in a static system. This is also a James paper. I just thinking about that. If the connect sulfide liquids in intercumulus space, and it have a high over magma, it high pressure. This high pressure can easily overcome the capillary pressure of this interface. So this this connect sulfide liquid can easily pass this crystal mesh, and then go to the bottom of this system. And this is also so many papers, so many works from Steve, and he do many struggles to see all these things about the downward percolation of the sulfide in the crystal mesh. But a hidden assumption here is that we always think that the sulfide can easily have a complete displacement of the intercumulus melt. This means the sulfide can totally replace displacement this interface, intercumulus space. Here I just this is in a weekend. I just have fun to do modeling. Here I think this is the crystal mesh, and the white circle maybe represent the crystal, and here is flowing the sulfide liquid. And we can see the downward percolation of the sulfide in this crystal mesh. Yeah, I think it's fit to our understanding about the downward percolation of the sulfide liquid. So I think, oh, it's right, it's no problems. And when it close to finish completely displacement of this space, and it's stable, these conditions. But when I try to increase, because here the silicon miles, I think is the Comatias. So the material's viscosity is also very low and close to the sulfide. But if I try to increase the viscosity of the intercumulate silicate melts, this didn't work. And firstly, I think something wrong in my setting of this model. But when I double checked all of the setting of the model, but it still didn't have downward percolation. The sulfide can just flow past this and they will not go down. So I think there's maybe something wrong in our previous understanding about this process. And then I found an old paper. It's an old paper to talk about the immersible displacement in the porous medium. There is an injection of the no whiting fluid. Here is just the sulfide. Injection into the whiting fluid. Here is the silicate melts in the crash mesh. And this work is just also doing the calculations and also doing the experiments. And they found 3 different types of this injection of this. One is the stable displacement like this, and this sulfide will totally displacement the intercumulate space. And one is the capillary figuring. This means the capillary pressure is most important. This capillary pressure depends on how the sulfide can transport this crash mesh. And one is the viscous figuring. Viscous figuring means the most things is the viscous of this intercumulate melts. Maybe you may think they are too similar, but they are just a little difference. For the viscous figuring, the sulfide can just go ahead and pass through this crash mesh. But for the capillary figuring, this sulfide maybe just can go back to form this circle and like don't like the this is just really different. So I think the previous work just considers the capillary pressure in the crash mesh, but overlook the because the difference between the viscosity in sulfide and in the silicate melts, this will drive some pressure difference across this sulfide melt boundary. There is a pressure difference along this boundary. It's driven by the viscosity difference between the sulfide and between the silicate melts. So this is I just thinking a small size how the sulfide can do in the downward populations. There are maybe 4 models: touch model, overlap model, and maybe sometimes the sulfide will snap off and form a new sulfide. And this is the breast model. And finally, I just built up a model to thinking about how to model the downward percolations of this sulfide liquid. Here, still the white circle is the crystal, and this is intercumulate silicate melts, and this is the initial interface. And above this interface is the sulfide liquid. And here, the top is the open boundary. I just add some stress and some pressure here. This means if we want to, there is a 1 meter sulfide liquid pour here, and we can just give the related, the corresponding pressure along this boundary, and we can see, oh, we can add 1 meter sulfide above these boundaries. And we also changed the different porosity, 13.3 and 14.4 and the 31 porosity. And here is the result. We can see if the melt viscosity is very small, this sulfide is blue. This sulfide can close to the stable displacement. But if I just increase the melt viscosity here, the 300 Pascal each second, it means the basalt viscosity. We can see there is some regions the sulfide cannot occupy. There is still some regions always contain the silicate melts, and we just show in the 2 model movies. We can see this is a low viscosity, and it seems like the stable displacement. Here is just like viscosity figuring, like the figure, just intrusion in the crystal mesh. And if I decrease the porosity, and there are so many regions that the sulfide cannot occupy. So I also show the modeling result. So you can see these regions may be difficult. The sulfide can be difficult to enter in. Yeah, and this is some pinch out, snip off of the sulfide. So in this region, it's very difficult to percolations in this system because this have very low porosity. So it pinch out of the sulfide droplet. And then another thing is if I just increase the height of the sulfide overlying sulfide pores, and if the sulfide is very thin, so it can just occupy the very small regions in the intercumulative space. And if I increase, even the overlying sulfide have 200 meters, still the sulfide cannot occupy all of this intercumulative space. So I think it's depend on this the capillary number and depend on the viscosity figuring, viscosity ratio. So we can say that because viscosity of the chromatia or picrite viscosity is very small, and there is a less difference between the chromatia and the sulfide liquid. So the sulfide percolations in this system will have a high saturation, means the sulfide can occupy a high fraction of the space. But if we're thinking about the viscosity of the basalt, the viscosity of the basalt is very large. So the downward percolation of the sulfide may be like viscosity figuring. So it can just occupy a small size, a small fraction of the space. So this is 3D results from a Jinchuan deposit, and the sulfide in this deposit, in this sample, is just like the viscosity figuring. Because if we're thinking about the crystal mesh, so the viscosity of the involved intercumulative melts, it should contain a very high viscosity. So I think our assumption that the sulfide should complete displacement in the space between the crystal mesh may be not always right for the metric or forming system. This may be not always right, I just say. And finally, we should also think about the upward transport of the massive sulfide liquid. Here is the knowledge experiments from Sandy, maybe GP papers. They think that the system, the magma chamber system, is two-layered. One layer is the silicon melts, and here is the sulfide liquid. And during this extraction of the silicon melts, it will take some part of the sulfide liquid, also doing the upward transport. But this experiment has some shortcoming because just two layers with the sulfide liquid and the silicon melt seemed impossible in a nature system. And secondly, this system should have some crystal gas and have some crystal mesh must in this system. And here is a new model for the crystal mesh, or the replacement of a new metal or new magma. We can see they build some, this is a crystal mesh, and they give a new magma replacement. And they give three stories to talk about that. If the intrude melt is denser than the intercumulative melts, it means injected magma is too dense, so it will just flow along the bottom of this crystal mesh. And if they have the same density, it just release some things. This region is released, but it will not change the solvent much. But if the intercumulative melts, for example, if the crystal mesh contains some sulfide liquids, this sulfide liquid is have very large density, and is denser than the intruder melts. And this intruder melts will carry some intercumulative mass. Here is maybe we will carry some sulfide liquid to go upward transport. But this is just ideas. We should still doing some experiments on body to confirm these stories. And finally, I just give a conclusion. It's just my opinion. For the sulfide droplet, I think the upward transport in ascending magma is a common story. It's very easy to occur. And secondly, if the system contains high water, high CO2, it will strongly enhance the carrying capability of the sulfide droplet in the ascending magma. It may be carry the 10%, 20% of the sulfide to take the upward transport. But for the compound droplet, it may be, I think that people we should take care about that. It may be easily break up in a fasting flow magma. And for the massive sulfide pore, the downward percolations should just occur as the viscosity figuring. Note the stable displacement. Secondly, maybe some process will drive the upward attraction of the sulfide liquid pore. It may be possible, but I think this process should occur in a very strong, powerful, very dynamic system. But we have talked about it. If this system is very dynamic, very strong, powerful, the sulfide liquid will quickly break up into the sulfide droplet. Return to this story. So this is the figure from the steel bands. So I think that the upward and the downward transport is not the opposite viewpoint. They may usually occur in different stage of the same conduit system. This means if the system, the conduit system at the beginning, it will have so many hertz. It may be very strong, powerful, and very dynamic. And in the beginning, the sulfide droplet can take an upward transport. And when along with the cooling, along with the crystal accumulations, and this system have cooling down, and this energy is powerful, is dynamic exhaust. And finally, the sulfide formed some liquid pore, and they will flow back and doing the downward transport percolation in the crystal mesh. I think they can occur in the same system. They are not opposite viewpoints. This is just my opinion. Finally, many thanks for your attention. I hope this make it clear. Thank you.